Welcome back. Life is so cruel. The day after spring break and the first day of spring. I think today's the first day of spring, isn't it? Something like that. And we have homework due, okay? Tonight at midnight. This homework 3.1, which is about these differentiation rules. And we're going to make things even a little bit more cruel. We're about to review those right now to remind ourselves of some of those things, so some of those rules, so that you can do really well on finishing this homework. And then we're going to go on to homework 3.2, which is just more of these differentiation rules. So we have quite a few of them to work through so that you'll be able to efficiently find the derivative, the rate of change function for most any sort of function that someone throws at you. So that's a new homework that is posted. Yeah, okay. And now one thing that's, because we had that week off, it's going to seem a little bit compressed, is test number 2 is coming up a week from Wednesday, March the 30th. And so I've already posted for you the test review for that one is already posted. So if you go to the Blackboard page under the sample test link, I've got that one posted. And I think it's pretty easy. But you'll make your own judgment about that. Anyway, it's ready, and by Wednesday, we will have, I think, talked about everything that's on that sample test that will be on the test a week from this Wednesday. Okay, so you should be have plenty of time to prepare for the test, but don't forget to start working on the test review, because that will really help you in preparing for the test. In addition to these homeworks. Let's start here as a warm-up. I want to review some of these differentiation rules, okay, that we learned right before the break last time, and we really talked about them pretty quickly. So we want to do some more examples, or let you work on some more examples here today, so that you can do well on that homework 3.1. Okay, so I'm going to give you all some review problems here to work on. Okay, all right. So so this is going to be a little bit cruel, because I'm going to be testing your memory there if you haven't got started on the 3.1 homework. But we've got John available here, so if he has to do some emergency tutoring during the class, he'll be happy to do that. Okay, so I'm going to give you a problem, give you a chance to discuss it with your shoulder partner, okay, or John if you need to, and then I'm going to ask someone to give their solution to this one, okay, so that we can review some of these very simple rules. And then we'll learn a couple of more differentiation rules today to go along with that, so you can start on the homework 3.2, okay? So remember, there are 4 or 5 rules that we learned last time, and these will really work in many situations. Not in every situation, though, I've got to caution you. Okay, they don't work all the time, so we've got to add some more rules to these rules, okay? And most of these are so simple that you can describe them in words. Most of them, not all of them, are so easy that you can describe them in words, but you really don't even need to, in most cases, remember the formula or even the verbal description of the rule, because once you've practiced these enough, they'll become second nature to you anyway. So the first rule says that the derivative of a constant, if you have an expression that's a constant, okay, that's just a number, right, okay, that doesn't have a variable in it, then its derivative is 0. Its rate of change is 0, okay, because constants are constants, they don't change, and so their rate of change is going to be 0, okay? So intuitively that makes sense, right, and that's correct. So in words, you just say the derivative of a constant function is 0, or the derivative of a constant is 0. The one that's really powerful, or seems like the most powerful of the group, is this so-called power rule. I can't give a verbal description of this one, but if you have a term that is a power, okay, so just a variable raised to a power, right, like this, then remember the rate of change for such a term, you find that just by, remember, bringing down the exponent, correct? You bring down the exponent and subtract 1 from the exponent, and that gives you the rate of change, okay? So this one we practice constantly. It occurs in almost every formula that we're asked to find the rate of change for. So this one you really get familiar with really quickly. It's really powerful and useful. But remember, this exponent in this power can be any number, okay, other than 0. Okay, of course, if that's 0, then what you really have here is a constant, all right, and then the constant rule applies. But this can be any number other than 0, and so that includes negative exponents, and that includes fractional exponents as well. Okay, so that really makes the power rule very useful in lots of situations. Okay. And then we have what's known as, this should be called the constant multiple rule. So if you have a term that's a constant times some expression, you find that you can just sort of keep the constant in the rate of change and find the rate of change of the rest of the expression. Okay, so constants really don't have much impact on rate of change functions. Okay. And then let's see, the last two here, the last one here is called the sum rule. So if you have a function, or it's actually the sum and the difference rule, if you have a function that's the sum or difference of terms, okay, then you can find the rate of change of that function just by finding the rate of change of each of the terms separately. Okay, that's what the sum rule says, right? So the derivative of sum is the sum of the derivatives, all right? So if you've got multiple terms in an expression and you want to find the rate of change of that expression, just find the rate of change of each of the terms. Terms means quantities that are added or subtracted from one another. Okay, that's why I keep using the phrase term here. So if you've got an expression which is the sum or difference of terms, multiple terms, can be more than 2, it can be 3 or 4 or 5, then you just find the rate of change of each of the terms separately, and that gives you the rate of change of the sum, okay, or the difference, all right? So again, those are just our most basic differentiation rules, okay? The easiest ones to apply and the easiest ones to write down, but they are really useful. They show up in virtually any formula that you want to find the rate of change function for. Any formula that you want to differentiate, you'll usually use one of these rules in calculating the derivative. All right, so of course, that's all rather abstract until we take a look at some examples. So last time we worked through several examples, and I want to go back now and look at some more examples just to help you review some of these properties. Okay, all right. So let's start with the very first one. We've got f of x equal 5 to the 10th power. And again, in every case here, we want to find the rate of change function for the given formula, right? Okay, so in other words, I'm trying to find, you can express that as f prime of x, right? Remember, that's how you write down, that's one notation you can use for the rate of change function, using the prime notation. Or you can use that more old-fashioned notation where you write dy over dx. Okay, that also means the rate of change formula. All right, so see if y'all can write down the rate of change formula for that one. 5 to the 10th power. Okay, now I've tried to make these a little bit tricky deliberately, so don't confuse yourself on what 5 to the 10th power really is, right? Okay, you don't have to calculate 5 to the 10th power, by the way. That's a really big number. Okay, but it's easy to calculate the rate of change without knowing exactly what 5 to the 10th power is. Okay. All right, so take a minute there and consult with your shoulder partner if you have to, or if you want to raise your hand and ask John, okay? And then I'm going to go through my trusty deck of cards here and choose someone. Looks like everyone's here today, so I'll get a chance to talk with most of the people that I call on here. I'm almost through one rotation of the deck. Oh, I've only got a few people left. That's good. Then we can start rotating again, okay? So if you haven't been on the hot seat for a while, you get your chance again here sometime during the second part of the semester. Maybe you'll get lucky and get a problem as easy as this one. What is the rate of change of 5 to the 10th power? Y'all got that one? Is that one easy? That one should be easy. All right. Let's call someone now, okay? So, Mario. Is Mario here? Carrillo? Hey, Mario. What'd you get for the rate of change of 5 to the 10th power? 50 to the power of 9, okay? Yeah, you took the bait there, Mario, okay? Because what you're remembering is the power rule, all right? So what you're thinking is to find the rate of change here. I just bring down the exponent, right? Okay? And then subtract 1 from the exponent, right? Okay? So you wrote this down, by the way, which is not 50 to the power of 9 in any case, because it's just the 5 raised to the 9th power, but the 10 is not raised to the 9th power also, okay? So if what you had done was correct, that would be 5 to the 9th power, whatever that is, and then later you would multiply times the 10, right? Okay? But this is, unfortunately, not right in any case, okay? All right? Because, all right, 5 to the 10th power... See, I deliberately was trying to trick you, okay? So that was mean on my part. But 5 to the 10th power, notice 5 to the 10th power does not have a variable in it. You see, that expression does not have a variable in it, right? Okay? So expressions that don't have a variable in it are called what? Begins with a C? C-O? Constant, right. Okay, I got you there. Yeah, those are called constants, right. Yeah, 5 to the 10th power is just a constant. It's a really big number, but it's just a constant. And what is the rate of change of a constant? Remember our very first rule. The rate of change of a constant is, that's the very first differentiation rule. Rate of change of a constant is what? 0, right. Yeah, 0. Okay, Mario. Okay, so yeah, the rate of change of a constant is 0. So if you have just a pure number that doesn't have a variable in it, okay, or a term that's just a pure number without a variable in it, the rate of change of that is 0, always. Okay, so you remembered the power rule correctly, but this is not an application of the power rule, right? Okay, so I rigged it like that to deliberately to fool you. How many of y'all were using the power rule there? So you're not alone there, okay, Mario? All right, yeah, all right. So yeah, that's an easy mistake to make. So what we should have written down here is just 0, okay? So don't make it harder than it needs to be, right? The derivative of just a number, and 5 to the 10th power is just a number because it doesn't have the variable in it, right? Okay? So, and the rate of change of that is always you just automatically go to 0, okay? Because constants do not change, right? That's why they're called constants. So their rate of change is going to be 0, okay? The rate of change is going to be 0, okay? All right, now, Mario, I'm going to give you a second chance on this one, okay? Because this one does involve, the second one, does involve the power rule, okay? Does involve the power rule here. But at first, it looks like it doesn't involve the power rule, Mario, because you have 2 times the cube root of x. So you're thinking, what does that have to do with the power rule? Cube root of x is not a power. But actually, the cube root of x is a power. So before we try to start finding the rate of change of this one, let me write it as dy over dx since I have it as y equals. All right, we need to rewrite that expression so that that cube root is a power. So how do you write the cube root as a power, Mario? Cube root of x is x to what power? 1/3, exactly right. So the first thing you're going to do when you look at this and you're asked to find the rate of change is rewrite that as 2 times x to the 1/3 power. Okay, right, that is 2 times x to the 1/3 power. All right, now that is a term now, that is an expression that has an x, right? Okay, so now to find the rate of change, now it takes a little bit more work. All right, okay, so find the rate of change of this one. All right, okay. So Mario got it started there. We rewrote that as 2 times x to the 1/3 power. And now let's find the rate of change of 2 times x to the 1/3 power. So if you're unsure, talk to your neighbor there, okay? Put your neighbor on the spot too, all right? So if you make a mistake, you can point a finger. It's his fault. Okay, well, the buzz has died down there. All right, so y'all seem very confident that y'all got that one right. Okay. By the way, getting this one right for me and getting it right for WebAssign might be 2 different things. I'll show you when we start writing down the formula for the rate of change. Okay, so George now is George Loza here? Okay, George. All right. Good thing you got here just in the nick of time, George. All right. So now you get to write down the rate of change for that one, 2 times x to the 1/3 power. So tell me what you write down there. So, forgot? Okay, so does your neighbor remember there? Who's your neighbor there? Does he remember? Okay, John, you're going to have to help them then. All right. So you got to do some emergency tutoring there, okay? So go over there and show them what they're going to do, okay? All right. While John is counseling, then this is a very important rule to remember, okay? Let's go on to the next one, all right? So let's go on to the next one. In a sense, this one is easier, although the formula looks worse. Okay, this is actually a formula that we had in one of our class activities, right? This is the function that models the amount that guys spend on underwear. Do you remember that formula? Okay, so it looks like a really ugly function there, minus 0.0063x squared plus 0.58x minus 1, okay, all right, and again, we want to find just the rate of change, all right, so see if you can find the rate of change for that particular function. Okay, so here we're going to apply actually multiple rules, all right? I think 3 out of the 4 rules that we learned. Well, how many rules did we learn? Did we learn 4 rules? Actually, we're applying all of them. So 4 out of the 4 rules apply in this one expression. Okay. So by the time we're finished with our doing derivatives, this type of derivative, you'll just be doing this one just like in your sleep practically, okay? I could, if I see you 15 years from now and at the Galleria and ask you the derivative of that, you'll be able to tell me that. So just like that, just be second nature to you. Okay, y'all made progress on that one? I'm talking about the underwear problem, number C there. All right, let's pick someone and see how far we made. Is Tim here? Tim? Going? No, Tim? You, Tim? Oh, okay. All right. You gotta wave at me and scream, you know. Okay. All right. So, do you have the rate of change for that one, Tim?
No, I don't know how to do it. Okay, all right. So, can you help him? Anthony, you're Anthony, right? Yes. Can you explain to Tim how to get the rate of change of that one? Do you have the rate of change of that one? Yeah, okay. So show Tim how to find the rate of change of that one, would you? Okay. Did y'all get it, George? Ah, okay. All right. So while Tim is working on part C, okay, which is actually a little bit easier. So George, you got the hard one, okay? George, you're going to explain to us the rate of change of 2 times x to the 1/3 power, which is really the same as 2 times the cube root of x. So what do we do, George? Yeah, the power rule. It's the power rule, right? So what does the power rule say to do? So you have 2 over 3. Where did you get the 2 over 3 from, though? That's correct, but that's right. Yeah, you bring the 1/3 down. Okay, you're going to bring the 1/3 down and multiply it in front here as a coefficient. All right. So you bring the 1/3 down. So you get 1/3 times 2. That's where you got the 2/3 from. Okay, right? That's the very first step of the power rule. And then what's the second step of the power rule? What do we do with the 1/3? Subtract 1, George, okay? So that's what you've got to remember. Yeah, they were all trying to tell you that. Okay, right. Subtract 1 from it, okay? That is the power rule. So if you can just remember those 2 easy steps, then you are about 50% of the way through finding derivatives, because they all involve, almost all of them involve the power rule, okay? So bring down the power, okay? And it doesn't matter if it's a fractional power at all. Bring it down in front, okay? And then subtract 1 from it. Subtract 1 from it, okay? So when you bring it down, you subtract 1 from it. But now, so that is really correct. So if you wrote that down on a test, that would be partial credit, because that is actually correct, okay? But we want to simplify it a little bit further from there. So, and you did that. So you multiplied 1/3 times 2 and got what?
We got
2 over 3.
X. No, the X in the bottom.
Yeah. Oh, not yet, though.
Oh, okay.
So what's 1/3 minus 1?
2/3.
Negative 2/3, exactly, yeah. Okay. All right. So that's step 2. All right. So all I did in that step was multiply the 1/3 times the 2, okay, to get 2/3, right? 1/3 times 2 is 2/3. And then 1/3 minus 1 is negative 2/3, okay, right?
Do you want it positive?
Yeah, we do want it positive, so, but we're just going to do it one step at a time here, okay? Right. So you now get a little bit more extra credit if you got to, a little bit more partial credit on a test if you got this far, all right? Okay? But now, all right, George, now here's what you're trying to tell me. How do I deal with that negative exponent? So how do I make you flip it right? Yeah, perfect, okay? So I would write this as 2/3 times, I would write this as 2/3 times what? So when you flip that, what do you get?
And you put the 3 times X.
Yeah, well, I'm just flipping this now, okay? So x to the minus 2/3 is 1 over x to what? To the positive 2/3. Okay? See that? Yeah. So I haven't done anything with the 2/3 yet. I just took the x to the minus 2/3 and I flipped it, right? Okay. So I got 1 over x to the positive 2/3 power, right? Okay. So a little bit more partial credit there. Now there's a couple of things left I can do here. First, let's take x to the 2/3 and let's rewrite that as a radical, because the original problem didn't have
a fractional exponent, right? The original problem had a cube root in it. So let's rewrite this x to the 2/3 power as a radical. How do you write x to the 2/3 power as a radical? Did you show him that, John? How you write x? Yeah, okay.
Put the 3 on the outside,
The 3 on the outside,
and then 2 on the inside.
2 on the inside, right. So yeah, so that's right. So the denominator there becomes the type of radical, right? And the 2 just stays as an exponent. So we would write that as, so I might be writing the steps different from what you've got written there. But I have 2/3 times, so this is 2/3 times 1 over, what'd you write now? So what?
3 on the outside,
3 on the outside, so that means cube root, right?
and then x squared.
Perfect, yeah, okay. And now you can go ahead and multiply the two fractions together, which is what you did at the end. So 2 times 1 is 2, and then you just multiply the 3 in to the bottom. So we have 3 times the cube root, so you can barely see that that's a cube root of x squared. There it is, okay, right? So the first step is really the key step. That's applying the power rule. That's applying the power rule. The rest of all of this is just trying to simplify your answer or rewrite your answer in the form that the original expression was written. So get rid of the negative exponent, write that as x to the 1 over x to the 2/3, and then take that x to the 2/3 and write it as a cube root. X to the 2/3 means the cube root of x squared. And so there we end up with 2 over 3 times the cube root of x squared. Is that too many steps? That's too many steps? Really? Okay. Well, they're going to all have about that many steps in them, so you've got to get used to it. Okay. All right. So dealing with negative exponents just means invert, and converting fractional exponents to radicals, you've got to get used to doing that. That's easy to do, though. Okay. All right. Great. Okay. Now, Tim, you're on. Okay. So you've also got the power rule, Tim. Okay, but a little bit easier application of the power rule, all right? So we want to differentiate this big expression, right? So, Tim, what do I do?
So you bring the 2 over in front of the first expression.
Right, yeah, so you get 2 times, what, minus all of this? 0, 0, 6, 3, and then what?
And then you subtract 1 from the exponent.
Yeah. Perfect. See, that's the power rule, right? So you get x to the 2 minus 1. Fortunately, that doesn't come out negative, right? That's just x to the first power, okay? So not too bad, all right? So there's the first term. Now what about the second term?
It has a power of 1.
1, right. So it's not written there because we don't write powers of 1, right? Okay, but we do the same thing, correct? So what do you do with the 1?
Multiply it by the term.
Yeah, multiply it by the term, so you write it down in front. So you have 1 times 0.58, and then x to what power? 0, yeah. Okay. And fortunately, still not negative. X to the 0th is still not, 0 is not a negative exponent, right? And what about the minus 1? We can't forget about the minus 1, but we might as well be able to forget about it because what is the rate of change of the minus 1? 0, yeah. Okay, so you're really just adding or subtracting 0 there at the end, right? Okay, because that's a constant again, right? 1 is very clearly a constant, and the rate of change of a constant is always 0. All right, now let's rewrite it. So what's 2 times this fraction here?
Negative 0.0126.
Negative 0.0126, and then what? X, and then what?
Plus 0.58.
Yeah, plus 0.58, right? Because x to the 0th power is really just 1, right? So that x to the 0th power, we can just throw it away, okay? And of course, the 0, we can throw it away. So that's it, all right? We just end up with, see, that was easy, just 0.126x plus 0.58. See that one, George, right? That one is an easier
version of the power rule, okay? Because you don't have to deal at the end with all those negative exponents and fractional exponents, right? Okay, so you're still using the power rule, but it comes out a little bit simpler. All right, now this I have a little bit of I have a problem in the margin notes here. Okay, it says find the value for this particular function. Find the values of x. Find the values of x where the tangent line is. Where the tangent line to the curve is going to be horizontal. The reason I'm interested in doing that is, let's remind ourselves, here is the graph of that function. Okay, there's the graph of that function. Remember, that was the function, again, that showed what men of a typical age spend each year on underwear. Okay, so this is from age 20 to, I think that went up to age 80. Yeah, up to age 80. Okay, and so we want to find exactly where, exactly the value for x where the tangent line is horizontal. Now we can see that on the graph because notice right here at the peak of the graph, right there, right at the peak of the graph, if you draw a tangent line right there, it's going to come out, well, I didn't draw it very well, but there it is, okay? Right there, if you draw a tangent line, right there at the peak, okay, it's going to come out to be horizontal right there, okay? So that looks like somewhere between, you can't read the numbers very well up here, but that somewhere between 40 and 50, okay, is where that x value is, okay? Somewhere between 40 and 50, there's the x value where the tangent line turns out to be horizontal, and that's the only place that I can see where the tangent line is going to be horizontal. But so what we want to figure out is exactly where is that value for x, okay? All right, so how can we find that now? Now that we know the rate of change function, how can we find that value of x where the tangent line is horizontal? Well, remember, the slope of the tangent line is the same as the rate of change, correct? The slope of the tangent line is the same as the rate of change. So what's the slope of a horizontal line? 0, right. So what we're trying to figure out is where is this rate of change going to be exactly 0, right? Where is the rate of change going to be 0? Because the rate of change gives us the slope of the tangent line. So all we have to do is take that rate of change, which is minus point, as Tim told us there, minus 0.0126x plus 0.58, and just set it equal to 0. Just set it equal to 0, okay? Just make the rate of change equal to 0 and solve that equation for x. Solve that equation for x. And that will tell you the x value where the rate of change is 0 or where the slope of the tangent line is 0, okay? All right, well, let's solve that equation for x. That's a very easy equation to solve for x now, right? Okay, because in this equation we just have x to the first power. So all we have to do is, I think, subtract 58 from both sides, right? 0.58 from both sides. So you get minus 0.58 on the right-hand side, and then divide both sides by minus 0.0126, right? Divide both sides by the minus 0.0126, okay? What does that turn out to be? So if you take minus 0.58 and divide it by minus 0.0126, what do you get for x there? Approximately. What now? 46.03? So very close to 46, right? Okay, very, very close to 46. 46.03 and essentially 46. So that tells us exactly what we were seeing in this graph, right? Okay, it was right here. Right here is where the tangent line was horizontal, and that happens to be right at x equals 46. Okay, all right. So, and that's what it looks like, okay, in the graph, all right? So we confirm what we see in the graph there, okay? The x value where the tangent line is horizontal is 46. Actually 46.03, but pretty darn close to just plain old 46. Okay. Now, see, that's very useful to us because, of course, that point right there is the peak point on the graph, right? Okay? And we're often interested in finding peak and valley points on graphs, okay? That's usually can help us answer questions that we want to answer, right? Where is the output maximum? Where is the output minimum? So finding where tangent lines are horizontal, see, they can help us figure out where are the peak points on a graph, where are the valley points on the graph, okay? And so we found out, without eyeballing it here, we found out exactly that peak point is right where x is 46, okay? So we could have guessed that pretty well just from looking at the graph, but now we can confirm it exactly. We don't have to just estimate it. We know it's exactly where x is 46. All right, let's try. Let's bump up the difficulty here. Okay.
All right, so here we have h of x is 4 minus 1 over 2x. Okay.
4 minus 1 over 2x.
Okay. All right.
So look, let me start you on this one. Okay. Let me start you on this one, and
Then that will help us with part E. All right. So we've got to get this written in, we've got to massage this into the correct form so that we can apply the power rule, okay,
or some of our other derivative rules. All right. So it's very easy now to find the derivative of the first term, because what's the derivative of 4?
0, right, because that's a constant, remember?
So the derivative of 4 is 0. So the problem is finding the rate of change of the 1 over 2x. But to apply the power rule there, you're going to have to get that written in the right form. And that means you need to get the x out of the denominator. Okay? So you've got to get the x out of the denominator. The power rule doesn't apply when you have x in the denominator. Okay?
So how do I get that x out of the denominator?
Of course, I have to do it fairly, right? Okay? I can't cheat to get the x out of the denominator. So how can I get the x out of the denominator in a legitimate way? Remember, that's x to the first power in the denominator, right? Okay.
So how can I get that x up out of that
Denominator. Yeah, write it as x to the power minus 1. That's the way to do it. But not the 2, okay? The 2 stays where it is, all right? Okay? So the 2 is going to stay in the denominator, but the x is going to go up, all right? So don't bring the 2 up, so don't get carried away, all right, and bring the 2 up with the x. It's just the x I'm going to bring out of the denominator. So the way we're going to write this is 4 minus, and we'll still have 1 over 2, okay? But when you bring the x up, you get x to the minus 1 power, okay?
See, if you have x to the first power in a denominator, then that's the same as writing x to the minus 1 power,
okay?
And now you can apply the power rule to find the rate of change.
So you cannot apply the power rule directly here, all right? But you have to rewrite the expression slightly first before you can find the rate of change.
Okay? All right, so now see if you can find the rate of change.
Now it's pretty easy. It's just a direct application of
The power rule. Okay?
So find the rate of change there. And actually, finding the rate of change itself is pretty simple. What may trip you up a little bit is then trying to simplify what the answer that you get. Okay, but you got to take first things first.
First, try to find the rate of change, and then we'll worry about simplifying it or rewriting it second.
No, just to the term that it's attached to. So the 4 is separate. Okay. So when you find the rate of change of the 4, we already mentioned, Zaman, that that's going to what?
A 0.
Yeah, so that you can just forget about, right? Okay, so let's try it here. I'm rushing y'all a little bit, but Jessica. Is Jessica here? Jessica. Oh, Jessica. Great. Okay. I knew that was going to happen. That was just fate. All right. All right. So Jessica prepped the problem for us. All right. So she's also going to help us find the rate of change. All right. So once you've got the problem set up right in the right format, Jessica, then it's really pretty downhill from there. So what's the rate of change going to be? So what's the rate of change of 4? 0, right? So if you want to, you can write the 0 down, but you can just leave it off if you don't want to. And then what? Yeah, so bring the -1 down, right? Okay, and that's going to multiply by -1/2 there, right? And then you're going to have x to the what? -1 minus 1, right. So you subtract 1 again, right, okay. So we end up here with, well, this just goes away, right, so I don't have to write the 0 again. What's -1 times -1/2? What did you say? 1/2, right, positive 1/2, right, okay. And then we get x to the -2, right, okay. So really that is the correct rate of change. So on a test, if you got that written down, you would really have substantial points, okay? The rest of this now is just simplifying or rewriting it, okay? And the reason I would rewrite this one is because the original expression didn't have a negative exponent in it, okay? If the original expression had the negative exponent in it, I would stop right there. But since the original expression didn't have the negative exponent in it, let's try to make the derivative expression look like as much as we can like the original expression. So how do I deal with that x to the -2? Right, so I get what? 1 over x squared, right, okay? And now you can just multiply these two fractions together. So nothing happens to the 1/2. It's just the x to the -2 that gets flipped, okay? So you end up here with 1 times 1 is 1, and then 2 times x squared is 2x squared. That's it, okay? And I don't think you can simplify it any more than that. So we just get 1 over 2 x squared as the rate of change formula, okay? Perfect. All right, now, so this part E now looks kind of similar, all right? Part E looks kind of similar. So we've got 2 steps here. First, we have to prep this. So we've got to get it written in the right form so that we can apply our rate of change rules. And that means this. I've got to do something with this. I've got to rewrite this 3 over the square root of x. So I've got to make that look different, okay? That's the first step. And then the next step is to actually find the rate of change, okay? All right, so let's try that in 2 parts. So first, I want you to try just rewriting the first expression. You don't have to find the rate of change immediately. You can if you want to. But first, rewrite the first expression so that we've got it in the right form that we can use to find the rate of change. And then so that's step one. And then let's find once we've got it in the right in the right form, the rate of change. Okay. So first, just try rewriting it. And what you're really going to concentrate on is that 3 over the square root of x. How do I change that 3 over the square root of x? And this can kind of help you a little bit in thinking about that. It's a little bit tougher, though. All right. So this is what you'll be practicing on your homework tonight, and then of course the test next week, right? These are the types of problems that'll be on the test. You can take a look at the test review to get a feel for that. Okay, let's start. Step one is just the prep part, okay? Because if we don't get that part right, then everything will be off, all right? So Sophia here? Where? Okay, Sophia, all right. So Sophia, you're going to help us now with just rewriting the expression, okay, so that we can apply the rules, right? Okay, and there's nothing to do with 4x. 4x is really straightforward. So it's 3 over the square root of x, and the first thing you want to do is you can't have square root of x. So how can you rewrite square root of x as a power? So square root of x is x to what power? Almost, okay. No, 1/2, right? Yeah, okay. That square root, cube root is 1/3, okay. Cube root is 1/3, so square root is 1/2. So you have 4x plus 3 over x to the 1/2 power. All right. So that's a great start, Sophia. But now we look and see. Oh darn it! I cannot have that x to the 1/2 in the denominator of that fraction. I've got to get the x to the 1/2 out of the denominator of the fraction. So how can I get it out of the denominator of the fraction?
Put it on the top.
Put it on the top with what? With the 3, but you have to make one other adjustment.
Leave the x at the bottom.
No, the x has to come up with the 1/2, right? Okay, but what about the exponent? So it becomes negative, exactly, right, okay? It becomes negative, just like this example, right, okay? So we would rewrite this as 4x plus, we bring it up to the top, so you're not going to have any denominator left, so I'm just going to write 3 there without a fraction, and then x to the minus 1/2, okay? So the positive 1/2 becomes minus 1/2, all right? Now we're just in great shape. So see, you've sort of got rid of the fractions. That's kind of our goal here, is to get rid of the fractions, if they have variables in them. If they're just numbers, then that's okay. But if you've got variables in them, we can't have that. All right, so here we have 4x plus 3 times x to the minus 1/2, and now we're in business. So now let's find the rate of change. Okay, so that's the next step. See if you can find the rate of change. And this is just a pretty straightforward application of the power rule, except, again, the simplifying part gets ugly. All right. Okay, let's try writing down that rate of change. So if we can get that, if you can get this rate of change written down, you're doing really good. Okay, because they don't get too much harder than this, at least for this set of homeworks. Okay. All right. So Zena, you're up. Okay. So help us write down the rate of change formula here for 4x plus 3 times x to the minus 1/2 power. So what's the rate of change of 4x? What? 4, right. That's just 4, yeah, okay. So the first term there, really easy, right? Rate of change there is just 4. Now let's work on the 3 times x to the minus 1/2 power. So that's the power rule. So what do we do first? That's right. So you bring the minus 1/2 down times the 3, and then times x to the what? Negative 1/2, right? Yeah, minus 1/2 minus 1, okay? So actually that is the rate of change, and the rest of this now is just all making this look prettier, okay? So we have 4 minus 1/2 times 3 is 3/2, okay? Minus 1/2 times 3 is 3/2. And then we have x to the minus 1/2 minus 1. How much is that, Zena? Negative 3/2, exactly, okay? So there's a little bit better, all right, okay? So you're getting, if it's on a test, right, you're getting a few more points there, right? You're getting from this step to this step. Now let's see if we can gut it out and simplify x to the minus 3/2. How can we rewrite x to the minus 3/2, okay? Yeah, put it in a fraction and in a radical, right, okay? So just leave the 3/2 and first write it as 1 over x to the what? Right? Yeah, x to the 3/2. And then how can you write x to the 3/2 as a radical? That's right. So that becomes a square root and of x cubed. All right? And actually, I'd be really happy with it right there. You can simplify square root of x cubed, though. And let me show you this for your homework, because x cubed, you can write that as x squared times x. X cubed is x squared times x. And the reason it's beneficial to do that is you can extract the square root of x squared. So the square root of x squared is just, you can extract an x from under the radical. So you can really write that as 1 over x times the square root of x. See, so I wrote the x cubed as x squared times x, and then square root of x squared is x. You get left with an x under the radical, but this square root of this x squared turns out to be just be x. So you can simplify that a little bit further. This is actually pretty good right there, but you can simplify it a little bit further, and on the homework they may want you to write square root of x cubed as x times the square root of x. And finally now, I'm just going to multiply into 3/2, so I get 4 minus 3 over 2x square root of x. So this would be fully simplified, okay? I really can't do anything else with that. Getting to this step, though, would be really pretty good, okay, in trying to write down the rate of change. You can really do anything with this expression that you can do with this one in terms of evaluating it, all right, with your calculator. Okay, let me save this. I have one more in my notes here, but I'll save this one, so I'll write this one down in the notes so you can look at that example in the notes when I post these. And I want to show you a couple of other simple rules, okay, today. And these are really easy, so they're not as hard to remember as the power rule is, or to apply, all right? The first set of rules are called the exponential rules, all right, and they apply to exponential functions. So an exponential function is a function where you have a base to a power, okay? The standard version of an exponential function is e to the x power. Remember, e is a constant, so that's not a variable. X is the variable here. E is a constant. Remember, that is an irrational constant. It's about 2.71828, but it's actually irrational. So the decimal expansion of the number e continues indefinitely, and it doesn't repeat. All right, so this decimal expansion goes on forever, and it actually never repeats. Okay, e is an irrational number. E plays a very special role in calculus. Okay, so you've probably seen the number e before in algebra class, and it's much less important in algebra class, but in calculus it's very important constant. All right, so in many applications we will have functions where you have the base e raised to a power, okay? And for that simple function, e to the x power, it has a very important property. Its rate of change is itself. That's the only function that has that unique property, okay? The rate of change, oh, except for, I guess, 0, all right, is the other example of that. The rate of change is the function itself. Okay, so if your function is e to the x power, then the rate of change is also e to the x power. Okay? Again, remember e is approximately this value. Now, many times you will also see exponential functions similar to e to the x power, but where the base is not e. Okay, so you might have some positive number base, but not necessarily the number e. So this could be any real number. Then the rate of change for a function like that is very similar to the rate of change of e to the x. The rate of change is going to be just the function itself, but then you have to multiply n times the natural log of whatever the base is. Okay? Remember that when you calculate the natural log of a number, that means the power that you raise e to get the number. All right? So for an exponential function where the base is not e, the rate of change function is just the function repeated and then times the natural log of whatever the base is. Okay? So you have to, this is a constant, by the way. All right? So you have to multiply in by this constant to find the rate of change. I'll show you some examples of this in just a second. Okay. So it's very easy. So rates of change for exponential functions are really straightforward, okay? Because the rate of change involves the function itself. If your function is the natural log function, it also has a very nice rate of change formula. Okay, which makes it very useful in calculus. So if your function is natural log of x, all right, natural log of x, then the rate of change is just 1 over x. Rate of change is just 1 over x. Very interesting, huh? Okay, so for a natural log function, the rate of change doesn't involve natural log at all. Okay, the natural log goes away, and you just get the very simple formula 1 over x. And again, we often in applications will have functions that involve natural log, so we need to know what their rate of change function is. All right, so let's take a look at just some simple examples here. Okay. I've got to caution you about one thing, though. Notice that this rule says the rate of change of e to the x. It doesn't say the rate of change of e with something else here with the x. All right, it's just e to the x, plain old vanilla e to the x. So if this were e to the 2x or e to the 3x or e to the 4x, this formula doesn't quite apply. Okay, so be careful about that. All right, so let's look at differentiating these simple functions. So suppose we have f of x is e to the x plus, and I just for fun there, I threw in square root of 2. So e to the x plus the square root of 2, and we want to find the rate of change of this function. Well, the second part is really easy because what's the rate of change of square root of 2? 0. See, that doesn't have x in it, you see, right? Okay, that doesn't involve the variable, so that is a constant, and so the rate of change of square root of 2 is just 0. All right, and now what's the rate of change of e to the x? So simple, just what? It's e to the x, yeah. It's its own rate of change function. All right, so the rate of change of e to the x plus the square root of 2 is e to the x plus 0. In other words, just plain old e to the x. That's such an easy one to remember, right? Makes that function really nice to work with. What about this function? Now here we have square root of 2 again, but times e to the x. So not just e to the x plus square root of 2, but square root of 2 times e to the x. Well, this is the multiple rule, okay? To find the rate of change of this function, you just keep the square root of 2. Just keep the square root of 2, okay? It's not added, so it doesn't become 0. So in the rate of change, you just keep the square root of 2. Just keep the square root of 2. And then what's the rate of change of e to the x? E to the x, right. So that function also is its own rate of change, okay? So in this case, the function and the rate of change function turn out to be exactly the same thing. Don't subtract 1, okay? So don't say that's, don't bring the x down and subtract 1 from the x, all right? Don't try to apply the power rule here. It's real easy to think about the power rule here, all right? But this is not, don't use the power rule here, okay? All right, what about 4 to the x? All right, that's also an exponential function because there you have a base raised to a power. All right, you have a base raised to a power. But the base is not e. 4 is not the same as e. Remember, e is about 2.718. So that's 4 is a little bit more than that, okay? So to find the rate of change formula, it's still very easy. You just repeat the 4 to the x power. You repeat the 4 to the x power, but then you have to multiply n by something here. What do you multiply n by? You remember? So that's this rule. When you have a base raised to a power that's where the base is not e, okay, to find the rate of change, you just repeat the function and then multiply by what? The natural log of the base. So we have to multiply n here by the natural log of 4. Now, if you want to know exactly what the natural log of 4 is, you've got to have your calculator handy, okay? So if you want a decimal approximation here, use your calculator to calculate natural log of 4. What is natural log of 4 to about 3 decimal places? What would that be? 1.386? Yeah, okay. So if you want to, you can estimate the natural log of 4, and it's approximately 1.386. But it's not exactly 1.386, so I had to put the approximate sign here because natural log of 4 has lots of decimal places in it, okay? But to 3 decimal places, 1.386. Remember, natural log of 4 means that's the power that you raise e to get 4. So what this tells us is that e to the 1.386 power is approximately 4. Okay? That's what that number means. If you take e and raise it to the 1.386 power, you'll get approximately 4. Okay? So this is the exact rate of change function. This is the approximate rate of change function. I would prefer the exact, but I think in some cases the homework is going to ask you for approximate. And if you're having to evaluate the rate of change function, so if you're having to plug in a value for x, and calculate the rate of change, you'll have to, use the approximate value. Let's try this one. So suppose y is, now this is a very weird function, so you probably would never see this function in practice, but this is just an example. Okay, so
2 to the x minus x squared. Notice those terms are different, okay? Here you're taking 2 and raising it to the x power. Here you're taking x and squaring it, okay? So those are, look, in a way, they're similar, right? They both involve 2 and x, but those are vastly different calculations, okay? Raising 2 to the x power and squaring x are completely different types of calculations. So suppose we want to find the rate of change here. Well, so how do we find the rate of change of 2 to the x? That's so easy, right? That is an exponential function. So you just repeat the 2 to the x and multiply by what? By the natural log of 2, right? Okay? 2 is not e. It's very close to e, but it's not e. E is 2.71828, so that e is a little bit more than 2. So since this number is not e, you have to multiply in by the natural log of 2. Now what's the rate of change of x squared? That's easy. That is the power rule. So what's the rate of change of x squared? 2x. Yeah, that's simple. That's just 2x. So there's your rate of change formula. It's just 2 to the x times the natural log of 2 minus 2x. And if you want to, you can get a decimal approximation for natural log of 2 using your calculator. It'll be a little bit less than 1. What about this one? 3 times the natural log of x. Well, I've got 1 minute. That's just enough time to finish these examples. So 3 times the natural log of x. So just keep the 3 because it's multiplied in there. It's not added in. If it were added in, you would just make that 0, but it's multiplied in. And then what's the rate of change of natural log, we said? So easy. 1 over x, right. Okay? So that one gives a very simple formula for the rate of change. This ends up being 3 times 1 over x, which is 3 over x. And finally, the last one here. So we have natural log of x plus 3x. Natural log of x plus 3x. So simple. What's the rate of change of natural log of x? 1 over x, yeah. So that one you can't forget. And what's the rate of change of 3x? 3, right. So you just get 1 over x plus 3. So that looks like that would be a terrible function to write down its rate of change formula for, but it turns out to be so easy. It's just 1 over x plus 3, okay, with these rules. What? Because that's x to the, yeah, that's x to the first power, right? So you bring down the 1, and then you get x to the 0th. But x to the 0th is really just 1. Yeah, okay. There it is, okay? So there's a couple more rules. So we're about halfway through our rules, all right? And this is the beginning of section 3.2, okay? So don't forget about your 3.1 homework, okay? I'll see y'all on Wednesday.